Good afternoon, everybody. My name is Donovan. As mentioned, I'm a partner at Deloitte. If you're wondering where the weird accent comes from, I'm from South Africa. Originally, I've been living in Prague for the last 7 years. I've been coming to Belgrade a couple of times over the last year, and I really enjoy it here. I love your food. It's better than the Czech Republic by far. But it's really good to be with you today, and I just kudos to Alexander and the team at DSC. This has been an incredible event.
Hello everyone, my name is Vladislav. Thank you for having me. As I have been introduced, I'm Vladislav. I am the technical lead at AI and Data in Deloitte, also based in Prague. I am leading the computer vision team there, and today we will be presenting one of the use cases that we delivered.
Great. In preparing for this particular pitch, I thought to myself, well, this will be a relatively mundane type of computer vision activity for the type of technical audience that I think is present at DSC. But if you look at some of the Gartner predictions around computer vision, and I don't want to spend too much time on this particular slide, but encircled there is basically how they predicted computer vision to be plateauing and really adding value into the workplace that we see. So it's with great honor and privilege that we get to work alongside our clients using computer vision technologies. We took a manufacturing use case specifically for you today because we can really talk about the value that it brought and quantify that, but we do a lot of computer vision work in transportation, in hospitality, in retail, and so forth and so forth. So it's great to see these type of technologies coming out of that hype cycle, really moving into production and adding real value to the workplace. So we're going to focus in a little bit on manufacturing specifically and around computer vision. And although I look like I'm 25, just kidding, I'm very old now with 3 children. For my sins, I spent a lot of time in manufacturing, probably the better part of 16 years. And I've been on assembly lines all across the world. And in South Africa, I spent a lot of time working for automotive clients, BMW, Volkswagen, etc., the tier 1 and tier 2 suppliers as well. And what I was doing once upon a time was what I would classify as peripheral integration. So I was doing a lot of integration of machinery, hydraulics, pneumatics, controllers, anything with a port, RS-232, 484, TCP, PLCs, I've connected into all of them. And let me tell you something, the worst possible thing to work with is a camera, right? So if anyone's ever worked in manufacturing, it is terrible. Temperature, lighting, speed. And I've met a couple of professors along the way as well. And I'm going to tell you 1 or 2 stories very quickly. One story, I worked on what we call visual inspection, right? So in manufacturing, you have this framework of quality control and visual inspection. So you're using cameras to do inspection. And I'll never forget, we were visually inspecting a dashboard. So in injection molding, you're building a dashboard. You're fitting clips onto a dashboard that holds the wiring harness for the vehicle. The operator takes this dashboard and he puts it into a machine that's got 6 cameras in it. The lights come on, the machine rotates, it takes a couple of photos. They spent 3 months trying to get this machine to pass the quality inspection on this part. And when I eventually got to it and I spent some time with the electrical engineer, what I could see they were doing was taking the control system on the camera that ships with the camera with some basic I/O on the back that you can trigger. And all they do is they toggle the threshold between the picture that they're trying to achieve versus the photo that's been taken. They're doing the similarity type of test. So when computer vision started to become a real thing, especially in manufacturing, I was super, super excited because it was just the next level of evolution around doing proper quality control. And we'll show you this use case in a second. I want to speak about quickly another story because I like stories. I'm a storyteller. I was in China at a tier 1 automotive supplier to a very prominent OEM. And I'll never forget, I was building a quality control system which was integrating into back-off systems across 3 production lines. And the idea there was to basically extract data from the production line and basically QC this data against the thresholds that had been put forward by the OEMs for quality. And there was one particular facility that was measuring torque and rotation and doing all sorts of weird and wonderful things. And my data analysis basically showed that this machine failed every single part that passed through it. Now in manufacturing, when you have a failure, generally everything stops. Because you see in the newspapers, when things go out the door, without the right quality control, they get recalled, and it's a very expensive exercise. No one wants to be in the firing line of a recall. And I remember presenting my results to the leadership at the time, who instructed the head engineer, PLC engineer, who opened 15,000 lines of PLC code, which is very boring, by the way. And he scrolled right down to where I told him the problem statement was, only to find out that someone on the late night shift, when people get really tired, commented out all the code that was doing the quality control check, and this machine was passing parts through, constantly failure. So when we talk about quality control, visual inspection, these things are really, really, really important in manufacturing. And we're talking about this particular use case and bringing computer vision to enhance the process, work with the operators, make sure that things are not being shipped out the door that are not meeting the right quality standards. And when we talk about efficiency and accuracy, it's exactly this. People get tired. People get fatigued. People do repetitive tasks over and over. Computers don't make those mistakes, right? We could talk about scalability and flexibility. In this particular use case, you'll see now that we're busy scaling out to 40 production machines across the assembly lines, and we will further scale to multiple plants as well. We're looking at talking about reduced downtime, reduced costs. In this particular use case, there's a part built every half a second, right? So when you're scrapping a batch, you're losing 20 minutes, 40 minutes, 30 minutes. In a production shift, that's a lot of money worth. So let's look at the particular problem statement. And I want to kind of give you a visual, and then I'm going to hand over to Vladia, who will take you through the technical inner workings thereof. We've got a very simple build process. We're basically pressing cold steel to make a very simple part, but we're doing this at high speed, and we're doing it in batch. So when you talk manufacturing, sometimes you talk just in time, which means you're assembling and pushing out the door just in time as the parts are being called off. In this case, you're building batch. They're putting about 1,000 parts into a box. And in this particular process, some operator comes, he's labeled the QC lead, and after they've packed 1,000 parts into the box, he inspects them and he says, oh, wow, this is not up to standard, and they scrap the whole box. This is happening something like 20 to 40 minutes after the build process is complete for this particular box or batch of boxes. So when we spoke to the client, funnily enough, the engineer said to us, well, we've been trying to solve this problem for 15 years. And you very clever Deloitte people think that you can solve it with a camera and some machine learning. And we said, well, let's give it a chance. Basically, within 30 days, we reduced the failed parts by 90%. And Vladia will talk to that in a moment. But at the end of the day, we set some metrics up with our client before we started, because as Deloitte, we always start at the value proposition. What value are we driving to business? Why are we doing what we're doing? We don't just like to play with technology for the sake of playing with it, but we really want to make sure that we're delivering value, and value that can scale for our clients, because that's really what's important. So the biggest issue for them was the amount of scrap. And for them, as soon as they scrapped this steel, it was wasted. They couldn't repurpose it, right? So it's money, absolute wasted. Not only then, they spent, like I said, 20 to 40 minutes in building this just before they're scrapping it. So they wanted to reduce the downtime. They wanted to increase the accuracy and efficiency of the process. And the great thing about this, sometimes as technical people, we just want to apply technical band-aids to problems. Sometimes the problems are process-related. So we see this quite often. I once used data science in a logistics problem. And what we did is we created data points across a warehouse, and we mapped out how people moved and how they packed on the warehouse shelving, how they shipped, how they loaded a flatbed steel onto a flatbed truck. And we were able to optimize the process of how they packed and how they shipped. And we were able to save almost €1 million a year just in ergonomics, if you want to call it that. So in this particular process, we basically re-engineered the process, which you'll see in a moment. So as I tried to illustrate earlier, very simply put, we build a part, we put it into a box, they build 1,000 of those, they box it, and then some gentleman with a magnifying glass, for the sake of illustration, comes and he looks and he says, we got to scrap this entire box, and they start all over again. They spend another 30 minutes recalibrating the machine, and they lose a lot of time. So when you look at a manual QC process, and I've seen this so much, the risk of human error is massive. When you just put a quality control system using computer vision next to a traditional operator, you see the natural attentiveness to what they're doing increase. even if you weren't necessarily replacing the operator in that particular space. Delays in process, increased wastage, slower throughput. If you've ever worked in manufacturing, just like my case in China, when the guy commented out the quality control, I bet he was under pressure to make sure the production line kept moving. Because when the line stops, it costs money. Someone's paying for it. And maybe someone would even be fining you at some point in time. So that slower throughput due to manual intervention is not desired. I'm going to hand over to Vladia to take you through what we actually delivered.
Thank you, Donovan. So, about the use case. We re-engineered the whole process by introducing a machine learning model with a camera into the workflow of parts being produced. And with that, we are not aiming to replace the operator. We are already helping the operators to focus their attention on the parts that require this attention. So instead of this manual QC, our machine learning model is checking all of those parts, and it's stopping the machine when faulty parts are starting to be produced. The operator comes, does the maintenance, and the scrap is much smaller. It's not the whole box, it's just maybe 5 to 10 faulty parts that have been produced. So here, what also is the benefit is the increased accuracy, because we were able to achieve almost 100% accuracy in terms of precision and recall with the detection. It's outperforming what humans can do, especially when they are tied on the night shifts. We are doing it real time, so by means of smart machine learning modeling and also compression of the model so that it is able to run inference once per half a second and also display this result, send it, share with the system. We are able to do it real time. Of course, it also means lower costs. We also have implemented a system that collects data for the client, because previously they only had just this large machine that didn't have anything. It was just connected to the PLC system, and right now it's integrated into the IoT system. The images have been collected so that they can be used for further retraining of the model and also for the analysis of the system. With that, we, for instance, discovered new defect types which were not known to the operators. We also are discovering patterns for predictive maintenance, so it's not just real-time quality inspection. The future of the use case is also to expand it to doing predictive maintenance on top. Here is a short introduction into the overall architecture of the tools that we are using. We developed the solution using Azure. It's not limited to Azure because everything is containerized, in our case, in Docker, so we can pretty much deploy the solution in any cloud infrastructure. Of course, we would need to re-implement the services for monitoring or deploying, but otherwise the workflow is kind of the same for any cloud platform. So what we have is the IoT hub, which is controlling the overall solution, the deployment of the Docker container that we have onto the edge device where the data collection is happening and the data sharing with cloud is happening. This edge device is also connected with the data collectors. For us, it's the camera, and initially we also experimented with depth cameras and LiDARs, but in the end we discovered that just having the camera is enough, and it's also cost efficient. There were also limitations concerning the space where we could put the camera, but about limitations we will talk a bit later. So that's it for the overall system. And it accounts for regular retraining of the model so that the model lifecycle is always active and has up-to-date data. And it also accounts for new parts that can be produced on the machine, because our overall target is to not just detect one individual part that's been produced on one single machine. The client produces a multitude of metal things, and they want to analyze on the same machine other parts, or they want to use the same kind of logic on other machines. So this architecture was accounting for all the things. To the modeling workflow, I think everyone who is doing data science is aware how developing a model works. Here, the most crucial part is the bottom of it, because the most complex, or the most complex part and most crucial part is communication of this whole machine learning-based model creation at the top with the inference happening on the edge device, where the model is deployed and predictions are being made, and also we need to communicate those predictions to the user interface so that operators can come and see for themselves what's happening. To the challenges. So it's not like working with good data sets from Kaggle or other open source with images where all the images are pretty good and well defined. We were struggling with the camera selection. We were struggling with those data collectors to select the most relevant one. The image quality was one of the issues we needed to resolve. We tested a multitude of cameras. We were using Intel cameras with depth perception. We used Keyence IV cameras. We used Cognex cameras, Baumer cameras, and in the end, we settled on one of those. One of the most crucial parameters that was influencing the predictions was lighting conditions, because if lighting is not stable, the predictions or the images that are being taken are considered out of distribution. And for that, we also implemented the logic. I will talk about it a bit later. Of course, connected to the image quality is the data format, and then the throughput of the solution, because the higher the amount of data to be transported, like using the uncompressed BMP format, then the lower the throughput is, given the latency constraints that we have, that we need to make one prediction per half a second. It was influencing the overall solution significantly. We also have constraints on the algorithm related to the latency, because it needs to be small, but still performant. And one of the biggest challenges that we encountered was not data science related at all, because we needed to integrate this system into the client's infrastructure. They have their own network, the so-called like technology network, that's isolated from the internet and isolated from their virtual network as well. So it needed to talk to both Azure, to this network, and to the to their virtual network where the company accounts exist, so that anyone can log into the solution and take a look at it. So we were resolving issues with firewalls, with defining which ports need to be open, how DNS should be set up in all of those parts of the solution. So it was one of the most significant and complex challenges to us machine learning engineers. Here is a summary of what was considered when we were selecting a camera, so the data source for us, the latency, the frame rate, the resolution, all of those challenges are mentioned and were discussed before. Our top performance at the end were the Keyence camera and the Cognex camera, because they were rather small, so that they can fit into this specific space where we are taking those images. And another thing that we discovered much later is the polarization. When people are taking pictures, they are not even thinking about such thing as polarization. But as we discovered, it can completely change the perception of the images that we see, because depending on how this filter is set up, or if it is there or not there, sometimes a human eye can't even tell if this picture is taken from the top or from the bottom of the part that's being produced. So we also did experiments with these polarization filters, and it was influencing the outputs. When we had the camera, we designed the box where to put it. This box needed to be small to fit into the production line. It needed to be able to be welded onto the rails on the conveyor. Over there, we have also the cables, and these cables are connecting the camera to the edge device, and also then the data is transmitted there to the cloud, to the inference, to the UI, everywhere. On the AI model architecture, in the end, it wasn't that complex to develop a model. It was more about resolving those challenges with data collection and also filtering the outputs, processing them. We have developed 3 models that are running at the same time. Of course, there was a whole exercise of model selection, but in the end, we have settled with the background removal model because we needed to remove all the rails or parts of the operator if they come, and also try to move something in the production. We also have this defect classification, which is a really simple ResNet model. We tried also MobileNet, EfficientNet, other architectures. This one was performing well for the images that we had. And we also implemented a logic of the out-of-distribution sample detection because of adverse events that are happening. Perhaps the glass filling of the box was just spoiled with oil because of the production. So there were some stains, and the images are not looking like the training set. They are looking like something else, and the model will predict randomly, depending on this spot of oil. Or maybe the operator touched the glass through which the camera is looking, and there will be spots that will also affect the performance. Or maybe someone comes and puts a different part to be produced on the conveyor, and we also need to be aware that there is something adverse. We need to change the model to a new one. We need to deploy another one. So for that, we developed an algorithm to just detect those samples using the energy-based, entropy-based as well, scores for auto-distribution detection. And with this set of models, we were able to achieve 100% recall and precision. So to the impact of this use case, I will first really briefly introduce what kind of data we are working with. This is just a visual representation of what was happening. Our primary objective was to focus on this type of defects when one detail of the pattern is just missing. But don't be confused by the size of this image, because in production, in real life, this defect is 0.5 millimeter big or small, or sometimes 1 millimeter. So the camera needs to capture it quite accurately. This is how the OK part is looking. And during the use case development, we discovered other types of defects. We will not talk about them right now. Sometimes the pattern is missing. Sometimes there are defects in the metal itself. So in September, we deployed the whole solution. We set up the box. We set up the edge device. And already at the beginning, the model was capturing all of the necessary defects with 100% recall, 100% precision. And it is not a miracle, because initially we did a lot of experimentation in the lab with the same box, with the camera, with all those parts. So we knew exactly what setup we need when we go in production. When we started discovering other defect types, we see that these defects are not happening often. It's just like 6 defects, 4 defects per day. But we are not capturing all of them because the model doesn't know what it is. It's predicting randomly there. But we implemented a sampling strategy. We implemented the retraining strategy. We implemented the class imbalance strategy into the retraining routine. And at the end, we started to achieve also 100% recall and precision after a few days of those iterations and data annotation. Now, I also wanted to mention that for sure there were some false positives they mentioned here in an aggregated form. And those false positives were just one-offs usually in the process. And by implementing business rules that, for example, we are only stopping the machine or raising an alert after 3 consecutive images, or maybe, let's say, also 5 images within 5 seconds predicted as not okay, then we are doing this operation. So these false positives were removed and cleared. Now I give the word to you, Donovan.
Great. In conclusion, we spoke about value and the real impact of something like this. While it might be simple from a model perspective, and there are some complexities in terms of implementation and integration, one of the biggest achievements here was that before, in this process, which has now been re-engineered, they were only detecting the defects 20 to 40 minutes after the production process was completed, and at that point, scrapping an entire box, right? Now, what we're doing is we're stopping the machine midway at the time of defect. They can do the necessary maintenance, recalibration they need to do. They scrap 2 or 3 little small pieces, and they continue to build. So we reduced the not okay parts by 90%. When we extrapolate that, you'll see on the next slide in a moment, across the 40 production machines, which we are now scaling to, that's a 1.2 million euro savings annually just in wastage. And if you look at the graph on the left-hand side, or sorry, in the middle, at the bottom, you see like a blue line and a green line. The green line is the number of, let's call it parts they're producing a day, and the blue line is the number of defective parts. And you can see over the first 3, 4, 5 weeks, that decreases almost to 0. So we really engineered the whole process, including finding new defects, which helped them to re-engineer the process even further. So as I said, we're scaling out to 40 machines now. We're predicted to save 1.2 million euro. I'm pretty sure when you take labor costs and all sorts of other things into account, there'll probably be even higher savings, and they will continue to scale this to a number of other facilities as well. Maybe Vladia will close quickly on architecture and what that will look like going forward.
Yes, so we are not settling with the current solution to be able to scale to 40 machines and handle those requests asynchronously in parallel as well. We need to improve the edge component parts and also harden the existing architecture to be able to handle this, to load balance it. We are also building an online inference endpoint so that we see if it performs better for us, because there are also trade-offs of running a large-scale operation on edge. You would need to have your server room, perhaps, there, or using these real-time endpoints in cloud. So that's also one of the considerations here. And since we are delivering this to the client at the moment, we are also operating this solution at the moment. So we are continuing on doing so and resolving the bugs, resolving the potential new feature requests, and operations of such solution is something I think each company that does automated quality inspection needs, because it needs to be handled by professionals.
Needless to say, the engineer that was trying to solve this problem for 15 years was quite impressed. So thank you very much for your time. I appreciate your time today. Please do find us on LinkedIn. We'd love to chat to you. Thank you.
And we can have some time for a few questions if you have them for our speakers. Yes, there is. Yeah. Okay. 2 questions. First, yeah.
Thank you for the presentation. A short one. Have you considered different lighting spectrum for when it comes to camera choice?
different light inspection.
Different lights, so not RGB, for example, but near infrared, which is less sensitive to the lighting changes and it also supports the reflections.
We tested different light setups. So we used ring lights, we used the spread light, but we have not used the infrared light. We just used the default one. Because in the end, we also needed to display the images to the operators. And right now, in the proof of concept stage, they would like to see the real image, what they see with their eyes. But the point of testing different lights or also different cameras is valid, and I think
we have really positive experience with near infrared in that regards, especially when it comes to light changes, if you cannot control light fully in the environment, so night, day, for example. And also a lot of great progress when it comes to use of synthetic data to train, to understand what's actually happening with the objects that go out of the production line. Thank you.
Thank you.
Sorry, here. In the first row here.
But there. Okay.
Thank you. Thank you for sharing your experience with this use case. I have two questions, actually. The first one is, the first time you had to train the model, how did you obtain the negative samples, let's say the scrapped one? And then I make the other one.
So our first iterations were in the lab environment with this box and cameras. We were not in the production line. So we had some samples from the client, and we were modeling these adverse events, modeling the negative samples as well, using tools like Hammer and the Peak, for example, to just make a small defect on the parts that they provided us with. In production, it was different because we just started running the solution there. On the slides, it was mentioned that we started it on the 4th of December, but the camera was taking images prior to that. We knew then when the machine was stopped due to the faulty parts being produced, so we knew exactly after which timestamp we have not okay samples.
Yeah, okay. Yeah, makes sense. So the first step was to build manually the negative sample, to assign labels manually, right? Mm-hmm. To pictures. Yes. Yeah. Okay. The other one is, the other question is, if you would push the inference process as much as you can, could this can be done to, for example, machines running at higher rate, like 1,000 pieces per minute?
Using a GPU, so for the modeling part, our current benchmark shows that we are able to predict one piece per 100 milliseconds. And this is without using the most powerful GPUs. We can downsize the model, and it really depends then on the images that have to go through the model and also on the defect sizes. We are detecting defects with half of a millimeter size, sometimes 1 millimeter size. If the defects are bigger, we can downsize, compress the images even further. We can use the smaller backbone model instead of this ResNet 50, which is quite big compared to others.
Okay, just for curiosity, if you can, what kind of product was this? Not Tiger, right?
So what kind of product was it?
Yes.
In terms of, how do you mean, sorry?
What kind of product you are detecting scrape on?
It's like a steel manufactured piece that's been punched, pressed. You mean the actual finished goods product?
Yeah, the product.
Yeah, it's like a steel strip, if you want to call it that. Sorry, I don't want to give away too much of what the product is for the sake of our client.
Okay. Thank you.
But basically cold rolled steel being pressed by a machine.
Yeah. Okay.
And with pattern there. So it's pressing some specific pattern that's then used somewhere else.
Okay.
There's some strength related to that pattern, so the teeth and how it fits together needs to be quite specific.
Thank you. Can we just have the final question on the right-hand side here? Thank you.
Thanks for the presentation. My question is related with the data labelers. Sorry, they are. I guess they are supervisors in the past, but they have relocated to this place or not?
So for the data labeling, we know exactly when the machine is stopped by the operator, so we know when the faulty parts are produced. So we don't need a large effort of data labeling. Otherwise, when we needed data labeling, we just have interns, students who have been given instructions and they annotated the data. They helped with that.
Okay, thank you so much.
Thank you very much. We have to wrap it up here, unfortunately. Thank you very much for your
Thank you.
answers and your presentation. This is for you, courtesy of the organizers. Thank you very much for being with us, Mr. Donovan Spronk and Vladislav Belov.